Okay, so tonight we're doing a very basic video on confidence intervals. I'm doing it a little differently tonight because I want to actually be able to type into the PowerPoint so you guys can see firsthand what I'm doing and how I'm solving the problems. Alright, so let's get started. We have three main types of confidence intervals. We have a confidence interval where we have a known population standard deviation, a confidence interval with an unknown population standard deviation, and a confidence interval for proportions. Now again, for the means, we're talking about population standard deviation. It doesn't matter about the sample population standard deviation. We want to know the population standard deviation. All right, so if we do know the population standard deviation, we use this first formula right here: x bar plus or minus z star sigma over the square root of n. Now, if the question or the problem does not tell us the population standard deviation, then we use this formula: x bar plus or minus t star s over the square root of n, where s is your sample standard deviation. Alright, and if we're dealing with a proportion, here we have our formula for proportions, where we're using the proportion from the problem plus or minus z star square root proportion or success minus times failure over n. Now we can take these same formulas and we can also figure out sample size. So manipulating the formulas, adding, subtracting, multiplying, dividing, we can actually solve for n, where we can find our sample size n. So if we're dealing with means, it has to be a problem with actual known population standard deviation. We can find our sample size. And if we're dealing with proportions, if we want to find our sample size, here's the formula for that. All right, so let's jump right into some examples, and hopefully you guys can follow what I'm doing. All right, so it says a college admission officer takes a simple random sample of 100 students. So let me start by underlining that. So we have 100 students entering freshmen, or a sample of 100 entering freshmen, and he or she computes their mean mathematics SAT score to be 458. So our mean SAT score, or our mean, is 458. It says assume the population standard deviation, that's important, is sigma equals 116. So this problem, they're giving us the population standard deviation. That means I'm working with that very first formula where we have the known population standard deviation. So question number 1, or question A, says construct a 99% confidence interval for the mean mathematics score for the intern freshman. Well, again, we're using that formula where we have x bar plus or minus z star, and then we have sigma over the square root of n. Alright, so in using that formula, I simply plug in everything I know. So in this problem, our x bar would be the mean score, so I'm plugging in the 458 plus or minus z star. Now the z star is kind of important because to calculate z star, you're actually going to do inverse norm on your calculator. Alright, so inverse norm, and in this case we're doing a 99% confidence interval, so we do inverse norm 1 minus 0.99 over 2, comma 0, comma 1, where our mean is 0, our standard deviation is 1. If you do that, you should get a z star of 2.58, and I'll write those steps in 1 second. So 2.58 for our z star times 116 is our standard deviation over the square root of n, which in this case our sample size is 100. Alright, now if you type all this in, so you do 458 plus all of that and then 458 minus all of that, you'll get a confidence interval of 428.07 to 487.93. And that's our confidence interval. In other words, we're 99% confident that the mean mathematics score at this university for their entering freshmen is somewhere between 428.07 and 487.93. Now, going back to that whole z-star issue, if I want to find z-star in the calculator, so hold on, z-star, all I have to do is simply type inverse norm, and I'm going to do 1 minus 0.99 over 2, comma, 0, comma, 1. And that's what I'm typing into my calculator for inverse norm. And basically that's giving you the area under the curve for a 99% confidence interval. Alright, next part of the question, it says, if the sample size were 75 rather than 100, would the margin of error be larger or smaller than the result in part A? Well, in this case, you're going to have a larger margin of error, because if your sample size, if you have a smaller sample size, you'll have a bigger interval. Alright. Now it says if the confidence level were 95% rather than 99%, would the margin of error be smaller or larger? In this case, it's going to be smaller, and it's because we're less confident. So the less confident that you are, equals the smaller the interval. So I'm less confident because the interval is so small. If the interval was big, I'd be super confident. It's almost like if you were guessing my age. If you guessed between 0 and 100, you'd be super confident that my age is in between 0 and 100. Alright, so you're very, very confident in that case. But if I gave you a smaller interval, like between 30 and 40, you might be a little less confident. Hey, maybe I'm 41, maybe I'm 29. You never know. You're a little bit less confident because you have a smaller interval. All right, the very last question says, based on the interval constructed in part A, is it likely that the mean mathematics score for entering freshman is greater than 500? Well, 500 is bigger than my interval. It's bigger than the highest value of my interval. My highest value is 487. So in my mind, I'm saying since I'm 99% confident that the mean falls in this range, I definitely do not think that 500, that a mean score greater than 500 is likely. So again, I would just simply say no, 500 is not in the interval. Alright, I hope that all makes sense. And again, you guys can email me if you have any questions on that. Alright, next question. It says, efficiency experts study the process used to manufacture items in order to make them as efficient as possible. One of the steps used to manufacture a metal clamp involves the drilling of 3 holes. In a sample of 75 clamps, so that's my N, let me underline that. The mean time to complete this step was 50.1 seconds. So that's my mean. Assume that the population standard deviation is 10 seconds. So again, they're giving us the population standard deviation. So just like the last problem, I'm using that very, very first formula. Alright, so let's work this out. Again, I'm using the formula that we used on this last slide. And I'm simply plugging in everything that I know. So my X bar in this example is 50.1 plus or minus. Again, I'm doing Z star, so I want to do inverse norm 1 minus 0.95 over 2, comma 0, comma 1. And again, that 95% confidence interval happens so often, it's one of those numbers you just want to kind of memorize. So for 95%, our Z star always be 1.96. Alright, and then you want to multiply that by, so times sigma, which they told us was 10, that's our population standard deviation, over the square root of n, our sample size, which is 75. Alright, if we plug all this into our calculator, doing the minus for the lower bound and the plus for the upper bound, we get 47.8 to 52.4 for our confidence interval. In other words, we are 95% confident that the mean time needed to complete the step for drilling the holes is between 47.8 seconds and 52.4 seconds. Alright, so the next question says, find the sample size needed so that a 98% confidence interval will have a margin of error of 1.5. So here they're asking for sample size. And so because they're asking for sample size, I'm going to go to that sample size formula again for means, because we're talking about the mean time that it takes. So that formula, if we go back to that slide here, that formula is given by n equals z star times sigma over m squared. Alright, so here, again, using that formula, I'm simply going to type in everything that I know. Oh, goodness. Alright, I'm going to type in everything that I know in this formula. So our n equals z star for 98%. Again, if I do inverse norm 1 minus 0.98 over 2, 0, 1, I get 2.326 times my sigma, which they told me was 10, over my margin of error that they're asking for, which is 1.5. And I want to square that. Alright, and so if I type all of that into my calculator, I should get something like 240.4567. Alright, hopefully you guys got that same number. Now the key to this is to remember to always round up. I don't care what number it is, you always round up to the next number, because if you round down, you're going to have a margin of error that is smaller than that. So you want to have at least the margin of error of 1.5, so we want to round up. And so if we round this up, our final answer is 241. Alright, so again, 241. In this case, we're talking about our clamps. Alright, and again, if you have questions on that, just let me know. Alright, next problem. It says a box of cereal, or boxes of cereal are labeled as containing 14 ounces. Following are the weights in ounces of a sample of 12 boxes. It is reasonable to assume that the population is approximately normal. Now, this is important, and we talked about this last unit. We talked about something called the central limit theorem. So we discussed with the central limit theorem that your sample size had to be at least 30. In this case, we only have 12 boxes. So normally that would not be considered a normal distribution. It's not greater than 30 unless the problem says it. So this problem had to tell us that it was approximately normal so that I felt comfortable using probably inverse norm, I don't know, but using normal calculations. So again, they're letting us know that it's normal. Feel good about that. I'm going to go ahead and work this out. Now, if you notice, they did not give us a population standard deviation. The only thing they gave us was the sample data. So using this sample data, the first thing I'm going to do is I'm going to go to my calculator. I'm going to go to Stat, Edit, and I'm going to type this data into List 1. Alright, so once I type this data into List 1, I'm going to go Stat, Calc, one variable stats, and I'm going to find the mean, and I'm going to find the standard deviation of this data set. Now, if you do this, you should get your X bar to be, I got 14.065, and for sigma, I got, or S of X, I should say, I got 0.614. Alright, and so with that, I can figure out my confidence interval. Now again, because they did not give us the population standard deviation, all we have is the sample standard deviation, I have to use the second formula, the second one. Alright, so that second formula, if I go back up here, that second formula says with the unknown population standard deviation, we're pretty much doing the same exact thing, except for this time we're using T star. Alright, now T star is a little bit different in the sense that it involves using your sample size. So in order to calculate t star, you're going to have to, in your calculator, go to inverse t. So the same area where you got inverse norm, you're going to go to inverse t this time. And the way you're going to type that in is you're going to say, so again, this is for t star. Let me change my type. T star equals inverse t. And then we're going to type in our confidence interval just like we did before. So 1 minus 0.98 divided by 2, comma, I have to type in my degrees of freedom. Your degrees of freedom is always 1 minus your sample size. So in this case, our sample size is 12. I have to do 1 minus 12, which is 11. Uh-oh, that did not work out good. All right, here we go. All right, so again, inverse t, 1 minus the confidence level, 0.98, divided by 2, comma, your degrees of freedom, which again is your sample size. I'll do it like this, 12 minus 1. All right, so we're not actually typing in 12 minus 1 equals 11. We'll just type in 11, but you just need to understand that's your sample size minus 1. All right, so once I get my T star and I have my X bar and I have my S, I can type it all into the equation. All right, so I get 14.065 plus or minus 2.718. That's what I got for T star. Let me write it up here. 2.718. And then we have times our sigma, which we found to be 0.614 over the square root of n. In this case, our sample size is 12. Alright, now once you get that all typed in, you should come out with a confidence interval of 14.017, comma 14.113. Alright, hope that all makes sense. So again, you need to find that inverse t first. And again, we're using t because we have an unknown population standard deviation. I think that's where a lot of you guys are going wrong. I've been getting a lot of emails asking about why it's not working when you do inverse norm. It's probably not working because it was probably an inverse t problem, not an inverse norm problem. Alright, so the last question says, based on the quality control, the quality control manager is concerned that the mean weight is actually less than 14 ounces. Based on the confidence interval, is there a reason to be concerned? Well, what do you think? Is 14 in the interval or is 14 not in the interval? Clearly, looking at this interval, the interval starts above 14. So I'm thinking that the weight can't be less than it if my interval, if I'm 98% sure that this contains my mean weight. So am I concerned? No, because 14 is not contained in the confidence interval. Alright, last example. A college admission officer sampled 120 freshmen or intern freshmen and found that 42 of them scored more than 550 on the math SAT. Right here I see they're not talking about average scores or anything like that. They're simply saying 42 out of the 120. Let me highlight this out for you guys. So 42 out of the 120 scored more than 550. This is clearly a proportions problem, 42 out of 120. So I'm using my proportions confidence interval. So the first question says, find a point estimate for the proportion of all intern freshmen at this college who scored more than 550 on the SAT. Well, again, that's just the 42 out of the 120. All right, and that equals 0.35. Alright, so the next question says, construct the 98% confidence interval for the proportion of all intern freshmen at this college who scored more than 550 on the SAT. So again, this is the proportion problem. I'm going back up here, and I'm using my proportion formula, confidence interval formula. Alright, so we have, here's our formula. Our proportion we already found to be 0.35 plus or minus z star. And so again, for z star, we're doing inverse norm. Inverse norm 1 minus 0.98 over 2, comma 0, 1. So I get 2.326 times the square root of, again, our proportion. So 0.35 times 1 minus 0.35 over our sample size, which was 120. Alright, and if I plug all this into my calculator, I get that this equals 0.249 to 0.451. In other words, I'm 98% confident that the proportion of students at this school, intern freshmen at this school, that scored more than 550 on the math SAT is between about 25% and 45%. All right, so the next question says, according to the College Board, 39% of all students who took the math SAT in 2009 scored more than 550. The admission officer believes that the proportion at her school is also 39%. Does the confidence interval contradict this belief? Well, 39% falls between 25 and 45, so no, the confidence interval, no, the confidence interval does not contradict this belief because 0.39 falls within the interval. Alright, I hope this helped you guys out a little bit. I hope this gave you guys a little bit more understanding on when to use what and how to use it. If you have any more questions, let me know and I will be sure to respond to your emails. See you on